Title of my talk is Brain to Speech, Decoding Intention and Generating Speech from Brain Signals in Non-Invasive Way. So, BCI is a technology that interprets and delivers a user's intention to the external world without relying on peripheral nerves or muscles. So, recent BCI research projects are like this. Human AI hybrid project by Neuralink. This aims for developing BCI communication to connect humans and computers based on AI. BCI for Kids, Cummings School of Medicine, aims for providing children with severe physical disabilities to enhance independence and participation. Wireless EEG headset enables to control games, art, and toys via brain signals. BCI ChatGPT integration by Synchron aims for integrating OpenAI's ChatGPT with BCI to restore natural communication for users with mobility disorders. AI-driven emotion and language predictions for users in real time and hands-free manners. So EEG is mainly used for non-invasive BCIs. This is a typical brain signal measurement method that records the brain's electrical activity via electrodes placed on the scalp. BTS, we call it brain to speech, is a technology that translates neural signals associated with speech production into audible speech or text. It enables users to generate intelligible speech by directly interpreting their neural activity. Types of speech can be categorized based on whether it includes voice output or physical movement of the articulators. Spoken speech is natural speech of speaking out loud. Silent speech is speech without voice output but with articulator movement. Imagined speech is mental speech without voice output and articulator movement. Spatial features of imagined speeches are mainly found on the language-associated brain areas over the frontal and the temporal lobe. Specifically, Broca's area is associated with speech production, whereas Wernicke's area is involved in the comprehension of speech. Frequency features of imagined speech are mainly found in the theta and low gamma bands, which are known to reflect the phoneme and syllable level process. Beta band is known to reflect the endogenous neural encoding process of imagined speech, notably in relation with the top-down control in the language domain. BTS research at Korea University is like this. We aim to translate users' imagined speech into voice output. Therefore, intuitive communication is possible just by silently imagining the speech. Deep neural networks were designed for robust decoding of imagined speech to convey various commands. This is a demonstration of EEG-based virtual home control.
Tom, help me.
I'm here. What can I do for you?
How's the weather today?
This is world-level non-invasive BCI interfaces.
Look, it's sunny today. Do you need any more help?
Please turn on the TV.
Okay.
Okay. Neural representation learning method is designed in our study to resemble the neural representation of neurons. Learning the neural representation from brain signals can contribute to improving the system's performance. Natural sentence generation framework is developed based on semantic encoder that is designed to learn various sentences by extracting the contextual features. Natural sentences could be probabilistically generated from the decoded semantic features using the large language model. Reconstructing diverse linguistic expressions is possible by adapting semantic learning framework that captures the intention of semantic features and clusters it into a single output. The reconstructed phrases are combined with the large language model to generate a variety of outputs to enable dynamic communication. Improving imagined speech decoding is possible using the diffusion model that learns meaningful features by removing the randomly injected noise to classify user intentions. Our model not only reconstructs corrupted signals, but also quantifies and learns from the reconstruction errors, potentially improving the overall accuracy and reliability of EEG processing. Therefore, multi-class classification performance was highly improved. Improving imagined speech decoding is also possible using signal enhancement method based on encoder-decoder framework. Overt speech-brain signals were used. Overt speech-brain signals were used as a supervisory signal to train the network. Therefore, it ultimately improved the performance of imagined speech classification. Expanding the vocabulary set of imagined speech is possible using metric learning framework, which is developed to learn unseen vocabularies. Therefore, newly added classes which have not been previously trained could be classified. This is a demonstration of controlling Google Assistant with the brain signals.
Hey, Google, how is the weather today?
It'll be sunny with a high of 87 and a low of 59. Right now it's 84 and sunny.
This is for turning the light on.
Hey, Google, turn the flashlight on.
Turning flashlight on.
Speech synthesis-based brain signals is possible by our generative model-based framework that reconstructs user's own voice from non-invasive brain signals. Domain transfer learning was applied to naturally map the imagined speech data into target audio. Therefore, our model could reconstruct voice using the EEG of not only spoken speech, but also imagined speech. Speech synthesis based on brain signals is, let me show you some demonstration. Okay.
Thank you.
This is the original voice. Let me show you the synthesized voice from brain signals of spoken speech.
Thank you.
Let me show you the synthesized voice from brain signals of imagined speech.
Thank you.
Sentence level speech synthesis has shown potential in using spoken speech EEG, which can ultimately provide more natural BCI communication. It applies transformer-based approach to train phoneme information and generate natural sentences. Silent speech have also shown the potential to reconstruct natural voice from EEG. Expanding BTS to sentence-level imagined speech is more challenging, since there is no proper ground truth audio in the case of imagined speech to train the generator. Therefore, transfer learning is applied to train phoneme features from EEG. It implies the potential of imagined speech-based speech synthesis by gradually expanding from phonemes to generate natural sentences. Continual learning method for expanded vocabularies has been developed by applying the self-supervised framework, which could dynamically adapt to changes in the word classes. As a result, we found that the potential of open vocabulary speech generation from non-invasive brain signals. Open vocabulary BTS framework has been developed using encoder-decoder framework that learns phonological information to generate unconstrained speech. The phonological decoding framework could reconstruct not only predefined classes, but also unseen sentences from EEG signals. These results demonstrated the feasibility of decoding phonetic features from speech-related brain signals. Let me show the recorded audio of the original voice.
Which theater shows Mother Goose?
Let me show you the synthesized audio reconstructed from EEG.
Voice generation is evidence.
Open vocabulary BTS framework is doing a diffusion-based method achieved notable improvements over traditional models by decoding phoneme sequences. From a restricted word corpus, the method successfully generated unseen words, showcasing its potential for open vocabulary decoding. KU NeuroTalk model is a novel deep generative network designed to synthesize speech from non-invasive and invasive brain signals. The proposed framework was validated using EEG words, EEG sentences, and SEEG datasets. Let me show you the demonstration for sentence level neural speech synthesis.
범인은 20대 중반에서 후반의 남성으로 보입니다. 범인은 20대 중반에서 후반의 남성으로 보입니다. 범인을 50대 중반에서 꿀판을 단서도 보입니다.
Talking face generation produces emotional talking face from audio and 2D images using generative feature aggregation models. Let me show the demonstration for talking face generation.
Don't forget a jacket.
I'm on my way to the meeting.
Will you tell me why?
So, lip-to-speech generation demonstrates limiting framework for silent speech recognition. It generates a talking face using conformal and transformer-based visual speech recognition that detects the location of lips in video and recognizes the linguistic sentences from the silent speech video. It encodes spatial features from aligned lip videos via ResNet 2D. The design of the architecture guides to accommodate the temporal features in the representations. It contextualizes the features with conformer and predicts linguistic sentences with transformer composed of encoder-decoder. Harmonic structure allows the simultaneous process of enhancing the extraction of long-range contextualization and local information. Let me show you the lip-to-speech demonstration.
배가 너무 아프다.
수술을 하고 왔어요.
Okay.
아침을 잘못 먹었다.
Brain to lip sync is developed for advancing PTS, which aims to reconstruct the talking phase from speech-related brain signals. The proposed model generates multimodal output of speech audio and talking avatar of the user from non-invasive brain signals. It supports patients' natural communication through digital avatar. A diffusion model-based VISIM decoding framework can learn visual speech intentions from speech-related brain signals. The reconstructed VISIM sequences contribute to dynamic neural communication by generating visual outputs such as talking avatars. This is the potential for real-world applications. It is being explored by applying our PT system to language-impaired patients. We collected EEG from a patient, trained our model in real time, and provide real-time feedback. This is a demonstration of PT system for Parkinson patient.
화장실 물 시계
This demonstration is ongoing work for BTS system for Parkinsonian patient. So we hope we can make a more complete demonstration next year. Okay. Thank you for your attention.
Thank you, Professor Lee, for an interesting talk. Now the session is open for questions. Any questions from the audience?
Thank you very much for the talk. So what instruction was given in the imagined task to the participant? Like when they're imagining, are they imagining saying the same thing over and over again, or just imagine without any, like what instruction was given?
You mean the questions or instruction?
Yeah, the question to the participant.
Yeah, so we have different levels of experiments.
Yeah.
In some cases, we give the word level experiment.
Mm-hmm.
And in some cases, we give some sentences level.
Right, but what they're doing is just thinking about that stimulus.
Yes.
That okay, and how time corrected? Or like, I have also another question about the timing. Is like, is it possible that we are decoding timing of various words, and or like what are we decoding on top of the
Timing, you mean?
Yeah, because various stimuli may have different lengths.
Okay, maybe I can ask to my PhD students. Seong, can you answer?
hello. Yeah, I understand your question, and that you mean the onset of the imagined speech.
Sure.
We instructed the participant to imagine as if they're saying, like imagine the movements and vocal sounds of the speech. And for imagined speech, as you consider that there's no exact onset, so we can't not find where the participant started to speak out. But we tried to align the alignments of the onset using the overt speech EEG. Okay. So in case of overt speech, we have the exact onset. Right, yeah. So we just tried to match the alignment with imagined speech.
Thank you.
Thank you.
Any other questions? Because there is a limit in time, we will end the session as it is.
Thank you.